Time of flight mass spectrometry can be used to find the relative atomic mass of elements. Define the term relative atomic mass. So this is the mean mass of one atom of an element. So one atom is crucial there. Compared to 1/12 of the mass of one atom, again, of carbon 12. Okay, so definitions, you either know them or you don't. Part B, a sample of tellurium is ionised using electron impact. To give two reasons why it's necessary to ionise the isotopes of tellurium before they can be analysed in a time of flight mass spectrometer. Okay, so if they are not ionised, then the first thing is that they won't be accelerated. And the second thing is that they won't be detected either. So it won't be detected. And there's your 2 marks for that one. Part C. The mass spectrometer of this sample of tellurium has 4 peaks. The table 1 shows the data from this spectrum. Calculate the relative atomic mass of this sample, giving your answer to 1 decimal place. So good exam technique here. Just going to give myself a little reminder down there for that 1 decimal place. And then to work out the relative atomic mass. So these are all percentages, so I'm going to divide by 100 at the end. So it's 124 times 10.5 plus 126 times 21.1 plus 128 times 36.8 plus 130 times 31.6, all divided by 100. So there's 1 mark for the working out there. And if you work that out to 1 decimal place, that gives you 127.8. Okay, part D. So 124 tellurium plus ion travels along a flight tube of length, so let's just pop a few things on here, 1.25 metres. The ion has a kinetic energy of that, so we've got the kinetic energy as well. We're given a formula and we need to calculate the time in seconds for the tellurium ion to travel down the flight tube. We're given Avogadro's constant, which is a big clue that we're going to need to work out the mass of the ion. So let's start with that. So mass of the ion is equal to, so the mass number is 124. Remember that is in grams, so we'll need to divide that by 1,000 or times 10 to the minus 3, and then divide that by 6.022 times 10 to the 23, and that gives me an answer of 2.06 times 10 to the minus 25. Okay, now I'm asked to calculate the time, so V is distance divided by time. Let's just rearrange that. So time is distance divided by velocity. Now I'm given distance, but I haven't got velocity, but I can work that out from here. So let's rearrange that. So I prefer kinetic energy is mv squared over 2, just makes it a little bit easier. So 2ke equals mv squared, so v squared equals 2ke over m, and then obviously need to square root that, so let's pop that in. So v equals the square root of 2ke over m, so let's put the values in. So that's the square root of 2 times, the kinetic energy is in the question, 1.102 times 10 to the minus 13. All divided by the mass, which I worked out earlier. 2.06 times 10 to the minus 25. And if I work that out for V comes out at 1.03 times 10 to the 6. So from here then, so I've got my V equals D over T. I've already rearranged it above. So the time is equal to distance divided by velocity. So the distance in the question is 1.25. Velocity, I've just worked that out. That gives an answer of 1.21 times 10 to the minus 6 seconds. Okay, so where are the marks for this? So there's 1 mark for calculating the mass here. There's 1 mark for rearranging that, including the square root. Obviously I've put the numbers, here we go. There we go. There's 1 mark for working out V. There's 1 mark for V equals D over T, which is up there, and then there is obviously 1 mark for the correct answer.